Okay. Can everybody see the slides? Yeah. Okay, good. So I would like to finish some leftover regarding union find. It's a very simple data structure, but in a lot of cases, it's underlying data structure that is used to check for connected components, which is one of the most simple version of checking for homological information of the data. So as we mentioned before, you can store a tree in a linear array by having sort of pointers pointing to the parent of each node, right? And then when we ended last time, we say, okay, what is a tree that is stored in this linear array? We can do one of them. So maybe let's do the one that has a root of 5, right? So I start with a root of 5. It has a pointer to itself. And then it has 2 nodes that point to it, which are its children. And one of them is 8. And one of them is 4. Let me just do this. Right? And then because there's nothing pointing to 8, 8 is now a leaf node. But 4, there's something pointing to 4, which is its children, which is 2. Right? And then 1 and 3 both pointed to 2. So those are its leaf node. Or 1 and 3. So that's it. That's how you recover one of those 3 trees. And of course, you can do for the rest of the other 2 trees. So there is the operation that is underneath the union find data structure. And there's a few functions that we're going to go through. And this is where, you know, I suppose most of you have seen pseudocode before. And then this is an example of the pseudocode. So the first operation is make set. So you have a node and you want that node into its own set. Okay. So what it does is to say, okay, all right, if I have a node X coming here, I want to make it into a set. If it's not in, of course, first of all, I need to check it's not part of my existing data. Then what I would like to do is to add it to the disjoint tree, disjoint set tree. What I would do is I would say I make a node where it itself is its own parent. So this is sort of the self pointer, right? You know, it has no other, it itself, its parent. And we'll also set up things like its rank and its size. Size is number of nodes in this tree, and its rank is 0 because it's just a root node. The second operation is called find. And find is basically a recursive operation to find its parent for a node, okay? So let's say I have this tree. Let's call it 3, 2, 1, 4. And let's say if I want to find the parent of node 3, what do I do? I mean, here there's a little bit of variation. Right now, I'm assuming I don't have a self pointer, but if I do have a self pointer like this, then this is to say it's not equal to itself, kind of, right? But in this case, what we do is to say, okay, let's see if I have a parent. If I do have a parent, which is this, right? I have something point to, then we are going to find the parent of my parent, okay? So this is a recursive call, is to say, if I have a parent, then I'm going to call it to find the parent of my parent. Otherwise, you just return itself is because it's just return, you know, depends on there. Like I said, there's 2 different things of storing. Version number 1 is to store the root such that there's no parent pointer. Then you return the root itself. Or if your root is stored with a pointer to itself, then you just, again, you know, checking that if it's not equal to itself, then it's also return itself, okay? So there's small variations whether your root node has a self pointer or not. But the essential part of the pseudocode is basically finding parents, parents, parents. So in this case, if I call the first round, V3 goes in, check if the V3 parent is not empty, which is 2. Then we're going to try to call the function again by finding the parent of 2. And then when we say, okay, is a parent of 2 empty? No. Then we are going to try to find the parent of V2, which is V1. And now if V1's parent null, yes, because it does no more parent, then we're just going to return V1. So that is finding your parent. Okay, so that's a find operation. Really what find does is that it just take a tree, and if you specify any node, it's going to find its sort of root, right? So it's essentially traced back to its ancestor, which is the root of the tree. All right, so question, if I have the following data structure in here, if I call find 9, right? 9 is the label of my 9th node. What is it going to return? Anyone?
6.
Exactly. So this is equal to 6. Okay. So that's fairly simple, but why is it useful? We have the find operation. There is something called a path compression. Okay. So this is a specific optimization I do, is that whenever I try to find my parent, if my parent isn't equal to myself, which means if I'm not the root, then I'm going to set the current parent to the parent of my parent. So what does this do? Okay, let's go back to this example. If I start with node, let's call it pink node. If I start with a pink node 8, okay? And if I go back to this, remember it says, whenever my parent is not the root, I'm going to make my current parent to the parent of my parent. What does this do? This is going to do a recursive formulation to say, before 8 is point to 1, after I call this function once, I'm going to remove my parent pointer to be pointing to the parent of my parent, which is 11. So I'm actually going to reroute my process, okay? And again, because it's recursive, what is ultimately happening is as I call this recursively, for any node that is not a root node, I'm going to record recursively again and again until at the very end, it's going to just point it to the root node. Okay, so what this do in terms of path compression is that before, if I want to find the parent or the root of my tree, I need to always perform a sequence of recursive operation, right? But if my main operation is just going to tell me who's my root, by doing this path compression, I'm reducing the cost because I'm going through once, and then what I'm doing is I'm just rerouting everybody to point it to its root node. So now if I ask, oh, who is my root? It's just one single lookup, okay? So that is one optimization that happened for the find operation, all right? Okay, so this is what's called path compression. But there is, well, like I said, this is union find. So it has two operations. One is union and one is find. So let's talk about both. There's two versions of union, okay? So the first version, which is the top one, which is the classic union, and then the bottom one is union by size. If I want to union sort of two node, and what can happen is, I have, let's say I have one tree, like let's say this is a very simple tree. And let's say this is 1, 2, 3, and then this is 4, 5. There's 2 things, and I'm going to call union 2 and 4, okay? What's going to happen is I want to union the component, or the tree in this case, that contains the node 2 and 4. So the first thing to do is to say, let's find the parent of those 2 nodes. The parent of those 2 nodes are 1 and 5. So it's checked, okay, the root is not the same, which means they belong to different tree. Okay, so I need to kind of glue the tree together. All right. So in this particular case, it says, okay, what is my x? X is my root of my first tree. My y is a root of the second tree, and x is not equal to y. Then I say the parent of x is equal to y. So what I do in this particular operation is I created this new arrow going from 1 to 5. So effectively, I'm gluing the tree that is rooted at x as a subtree, which is now a subtree of the tree that is rooted at y. So that's the operation. So if I redraw the union result, it's going to look like this. All right. So that is what it returns. Okay. And of course, assuming, I have this, I store both trees in this array, then it's just simply changing a single pointer to kind of glue those things together. If my question is try to recover my number of connected components in my data, I go from 2 components to 1 because those 2 trees merge into 1 tree. Okay, so however, when you actually just union like this is pretty arbitrary. I said, well, I basically attach the first tree to a second tree, okay? But now there's some argument to say I want to kind of attach, based on their size, whether is a tree y attached as a subtree to x or x as a subtree to y, rooted at y. So in this case, you can just do a little bit fancier to say, well, if the size, right, remember each of the nodes store a size, if the size of my tree, if the left tree is bigger than the right tree, then I'm going to exchange those 2 trees. So I want to always attach the small tree to the large tree. All right. So if x size is smaller or equal to the tree y, then I don't do anything. I attach x to y. Otherwise, I'm going to switch them. This is just a switch notation. I'm going to switch those 2 trees, one to be the x tree, one to be y tree, and I'm always going to attach the smaller tree as a subtree to the bigger tree, right? So that's that. Okay. So union find has some different variations, as you can see, but ultimately it's going down to this. So for example, in this case, if I want to union the node 8 and the node 4, what is the result of calling union by size? Do I have a volunteer?
6 will be the root.
6 is going to be
the root of the union tree, and the left hand. Okay, so and the other tree will be the tree with the root 15 will be the subtree.
Yes. This would be the result, right? Because I always want to attach, because the size of the tree, so first of all, when I find the root, x is a root of 8, which is equal to 6. Y is a root of 4, which is 15. And I'm looking at the size of it, okay? And the size of it is the size of the tree stored there. So essentially, I would like to know is which one is a smaller tree. In this case, the left tree is bigger, so I want to switch them so that the smaller tree is always attached. So I'm attaching the smaller tree, which is right-hand side. All right. Okay, so that's union find. That's pretty simple. Okay, so that is a little bit left over from last lecture. Now let's spend the majority of today talking about TDA and machine learning. And Some of you, maybe a few of you have seen this before because I've given this research talk a few times, but I think it's a good example of what you can do using topological data analysis and machine learning, especially what can you do using topology to study activations of deep learning models. It's just one example. As I mentioned, there's many other existing examples. So I'm hoping to spend some time this week to discuss those applications, and that will help you formulate. Well, it's not required for your final project to be TDA and machine learning, but if you're thinking along this direction, this will be some examples of literature. Another reason I also want to give this talk is because it also uses this topological descriptor called MapperGraph. And then our first mini project is going to be based on MapperGraph. So I want to give you guys a taste of what this structure is. It's one of the most widely used tool. And the interesting thing that it also comes with a bunch of parameters. So it's going to take a while for you to understand what's the strength and weakness of this particular descriptor. But I want to start by actually talking about its applications. Then we'll go back to the mathematics behind it. And it's still a very active research area to understand the mathematical property of this particular descriptor. All right, so without any delay, the first thing that this is the work I kind of advertised at the first lecture. This is a recent published paper that I'm involved with, but I think it's a good example of how you use topology to probe deep learning models. Okay, so there is sort of a live demo, and there's also code you can play with, and so on. And it's done by my PhD student Achet and Saurabh, who's now postdoc, and Nising is actually an undergrad student who contributed equally to this work. So, so some sort of acknowledgement, funding agency, and so on. So, and specifically, we had natural language expert who provided a bunch of expert feedback using our system to study BERT, which is a neural network used in text classification. And we'll describe that soon. All right, so first of all, how many of you have sort of been exposed to deep learning? Raise your hand, or you can raise your hand through through the Zoom. Thank you, guys. So a subset of you, okay? So my class is not on deep learning, but if you have never sort of be exposed to deep learning models, let me know. I will put a bunch of reading materials, right? So don't be scared if you have not experienced this before. I mean, for today's lecture, I'm just going to describe it on the high level. Okay. So here is a model of a very highly simplified picture of Inception V1, which is a neural network used for image classification. And it's also called GoogleNet because it's developed by Google initially. And then there's other sort of models in this space. For image classification, there's also ResNet. And then for text classification, there is BERT, right? So those are just different models of neural networks that is used to perform different tasks. And the framework I describe here is not constrained to those neural network models. Okay. So specifically for Inception V1, I'm going to simplify it a little bit. I'm going to focus on sort of 9 layers of this neural network. And to be fair, each of this layer, as you see, there's 9 different boxes, is actually in itself is actually, you know, multiple layers internally. But right now, I'm just going to treat it as one single layer. And it will become clear later why I do that. Basically, I would like to probe the neural network by collecting what's called activation vectors. And I'm going to study the topology of those activation vectors. Okay. So this activation vector sometimes are also called representations, right? So when you actually learn a neural network, that there's kind of weights attached to the neurons in each layer, and you can sort of look at what is a weight attached to a particular input. So let's get backwards, like sort of very high level, right? So one of the main challenge in deep learning is about interpretability. So if you train an image classifier and it has like 99% accuracy to tell between cats and dog, right? But the question is that how does it work? Why is it working the way it's supposed to? So what representations have those neural network learned that could be made human interpretable? That's sort of one framework of the notion of interpretability. So the framework we are taking is to say, let's say my image classifier is already pre-trained for classification tasks. In our case, GoogleNet is already trained over more than 1 million images. So it does its magic. Now, if I probe this neural network, what I'm going to do is I am going to obtain the activation vector by feeding it with a particular input. Anka, you have a question, go ahead. Oh,
sorry, I don't have.
Oh, okay. So your hand is raised. So I guess it's still previously. That's fine. All right. So now with a large number of input, let's say I'm going to probing the neural network with, say, you know, 1 million or 300K images, which is what we did. We are going to try to get the activation vector for each of those images. And then we're going to study how those activation vector looks like for a single layer and also across multiple layers. So once we have those activation vectors, the main question is, how are those activation vectors organized with respect to the type of images? So in another way, what is the shape of the space of activations? Okay. And then there's a few ingredients. And the first ingredient is we are going to collect the data from the neural network, which is what we call neural activation vector. And for those vector, we're going to treat it as a high dimensional point cloud. So that's the first thing. The second thing we do is we're going to apply a mapper graph as a topological summary of this high dimensional point cloud. And this is where the topological tool comes in. What you get is you have this high dimensional point cloud, you obtain a graph-based representation of this point cloud. And then we can explore this, this graph-based representation to try to see if there's anything that is interpretable from this topological summary. And there is sort of an online tool you can play with. All right, so the most interesting part to take away from this project is that we can capture topological structures of this graph. Specifically, we're focused on branches and loops. And specifically, we're going to talk about branches because in some sense, the branches corresponding to bifurcation of the model that start differentiating different classes of images. Okay, so what I think is a very interesting topological perspective to understand how a neural network sees a particular input. Okay, so we're hoping this will be an interesting toolbox to be used to study neural network, and specifically later on for maybe architecture diagnostic and anomaly detection. I mean, this is sort of a speculative for its potential usage. Right, so let's give an example. So here is an interface of the tool. In the middle right here, this picture you're seeing is this mapper graph. And if I click on each node in this mapper graph, it's going to show a box which said this particular node contains all the activations of a bunch of images, where the top 3 classes of images is coming from tiger cat, leopard, and coyote. Okay. So, and then in this part here on the right-hand side in C, well, actually, I shouldn't recolor it. It's showing sort of examples of images that is in these 3 classes. The first row is 4 examples of tiger cat, and then third row is 4 examples of the coyote. All right, and then the D panel is what's called feature visualization. And what it does, it says, okay, I'm going to create a futuristic picture that give rise to this activation. And then it's going through an optimization process itself. It's just looking at essentially what is, if I don't know what my image is, but I know the activation, what is a picture that I can synthesize that give rise to a similar activation, okay? So, and then this picture here, right here, sorry, to the right-hand side of this black box, this is what we call the average a feature visualization, which is what I'm taking all the activation vectors that belong to that node. I take the average of it, and I do reverse engineering to try to find the image that give rise to the same average activation vector. So what it does, from a sort of practical perspective, is try to give you a sense is what sort of image feature give rise to all the activations in this cluster. And you can see it does look a little bit futuristic, but what you could pick out is actually the texture of those animal. Like, they're all having those dotted, spotty kind of texture from their skin of those animals. So this activation vector looks like this. All right. So, okay, so this is a good time to take a 5 minutes break, and I'll be back in 5 minutes. Go stretch your leg, and we'll come back and finish the second half. And feel free to ask me questions if you have any at this moment.
Hi, I have one question.
Yeah, go ahead.
So what does those feature vectors correspond to on the neural network that you train? So is it a layer or it's some back propagation?
Yeah, so here is a picture. If you have an image, right? This is an image with dogs, I believe, right? And this is a particular layer that I care about. And what you see is whenever you fit an image through the sort of convolutional neural network, it's only a patches of those image that go through. So in this particular case, this particular example, it has an 8 by 8, so it has many patches, right? So it has 64 patches. But if I take any one of those patch, I would be able to obtain what we call activation vector. So here, what the arrow is pointing, one of those vector is what we call activation vector. It's corresponding to sort of the weights attached to all those channels associated with it. One particular example you can see, if I, do I have that example? Oh, I might have, in my older slides, I have example where essentially, if I flatten this image, let's say this is, a dog image. I'm horrible in drawing a dog. Let's say this is my dog image, and I have a particular patch surrounding the head of the dog. And then what this returned is, a value, let's say it's have 512 dimension. So it's going to be something like 0.1, 0.2, 5.3, blah, 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 right? So it's going to be sort of like this weight vector attached to that channel. And that's what I mean by activation vector. Okay.
Yes.
Yeah. Okay, so I think we have our break starting 9:42. So 9:43, 3 minutes.
Oh, by the way, I think that you didn't directly answer my question. My question is, so what the picture we're looking at, can you go back one page? Go back one page, to page 8.
Yes.
Page 8.
Oh,
I mean,
page 8.
Yeah, there is page 7 actually. Sorry.
Yep.
So in the bottom right corner, there's a few features. What are those? My question.
Oh yeah, feature visualization. So this is not our technique. This is a known technique. So what it does is to say, okay, if I know the activation vector of a particular image, right? What can I do to kind of reverse engineer an image that will give the same activation? Okay.
Yeah, my question,
so this is what the feature visualization does. It says, if I know what my neural network activation looks like, I would like to reverse engineer an image that will give rise to the same activation. Okay. Of course, you're not going to, most likely not going to generate a very realistic looking picture of a dog or a cat. I mean, in this case, they're more like tigers, right? Yeah. But I'm going to generate an image that will give rise to a similar activation. So it's an optimization process that is actually, if you go to the paper, it's going to, there's a reference in there of how people do that. But of course, first of all, it's a reverse engineering. 2 is optimization. So of course, what you get is not sort of the unique answer. It's just some images that give rise to this activation. But what the hope is, it's going to try to tell you what type of image feature give rise to this activation. So if, for example, for all the, so those are examples of the feature activation that is generated from the class of images in this node. You know, they all look kind of interesting, but what you can pick out, you can see some texture in there, right?
Yeah.
But also you can see even some of them even has like eyeballs, like for example here, there's some eyeballs, right?
Yeah.
So we'll see some of other examples later, and it's sort of like debatable, you know, how much do you trust those things, but it's just trying to give you a sense of what sort of features is being picked out by the classifier. That's what it means.
Great, thank you. And one more question. So what kind of activation you are optimizing for? The 111, the all one activate?
No. So in the middle of this picture, I'm taking the average patches activation. This is taking all the average activation of everybody. This example, I just want to give actually sort of feature visualization of a single of the patch from a single image. Okay.
Right. Okay.
Yeah. All right. So. Okay. So. All right. Now let's, hopefully people are back. Now let's look at the pipeline. Okay. The pipeline is as follows. I start with a network that is pre-trained. So in this case, my pre-trained neural network is an image classifier inception V1. And later on, we also did ResNet 18, which is another classifier and it's slightly simpler. But they're all pre-trained. So now with the pre-trained network, I can probe the pre-trained network by putting a bunch of input images and then collect what we call activation vector at a particular layer. So for inception V1, there's 9 layers. So I'm just going to focus on one of those layers, and I'm going to see how does my network at this layer react to my input image. And I collect something called activation vector, which I will describe very soon what they mean. They are basically high dimensional point cloud. Each of them is a high dimensional vector. I collect a bunch of them that become my point cloud. And then given this point cloud, I'm going to obtain what's called mapper graph, which is a topological summary of this point cloud. You know, without describing the mass, you can see that, you know, this point cloud example I gave is a point cloud sampled from the silhouette of a snowman, okay? It's a bunch of points on the silhouette of it. And then the mapper graph sort of is a skeleton of it, but still capture roughly some interesting information. It still recovers, for example, the hand of the snowman, even though it misses the finger of the snowman, but it still kind of captures the head and then the body, right? So in a way that the mapper graph is a quick sort of summary of the shape of my point cloud. I mean, it's an approximation of it, but it captures some of those important structure, okay? The other thing I do want to note is that you can do this for every layer. So you can study this topological structure across the 9 layers of the inception network, okay? So here is, before we go into detail, here is a sort of like an example of the type of thing you're going to see. This is a zoom in view for ResNet 18, and it's trained over CIFAR10, which is an image data set. CIFAR10 means that there's like 10 classes of images, such as horse, deer, frog, airplane, truck, car, and so on, okay? But this is a particular zoom in of this mapper graph in the middle, which I'm going to show you how this mapper graph is capturing the separation between classes. So this is the last layer of ResNet 18, and then the middle picture is a mapper graph that is summarizing the activation vectors. And you can see there's a branching happening. On the left-hand side is a branch where all the images, so I'm looking at the image, say, let's say B. B is an example of images that is giving activation in this cluster of activations. And all the images is deer, okay? So, and then of course, C, same thing with C. If you look at C, I'm again giving examples of images. Of course, here's a little bit low resolution, but you can still see it. Those are images that's also deer image that give rise to the activation in that cluster. The right-hand side now is horse image. For example, from node D, you can see that those are all horse images, which give rise to the activation, and so on and so forth. So what is happening? This is a bifurcation between activations that come from deer image and activation coming from horse image. And then at the branching node, which is my node A, you can see on the left-hand side, it's roughly 50-50 split. There are roughly half of the images in there are from horse and half of the images in there are from deer. So node A contains activation vectors that is coming from a mix of classes, okay? So in some sense that there is a connection between branches versus class separations in some way that we're interpreting the neural network as to say, okay, at the end of the day, it achieved pretty high classification accuracy to separate horse images from deer images. And that separation is sort of indicated through this branching structure, because there are existing images where the neural network is not doing the perfect job of separating, okay? Now, let's also talk about the overall pipeline for image classifier. Like I said, this framework is generic for any sort of neural network as long as you can collect the activation vectors. So in this case, this neural network is used for text classification, and it's called BERT, right? So what it does is it's also pre-trained. So instead of probing it with images, I'm going to probe it with sentences. So before each of the input is an image. Now each of the input is a sentence, okay? And for the sentence, what's going to happen, for example, one sentence I'm probing the neural network is, she invited me in for tea and a massage, okay? Well, this can't happen until pandemic is over, but we're probing the neural network with a sentence. And one specific thing I want to highlight is the word me, right? So this is considered a token in the sentence. And when you probe the BERT with a sentence, every single word in the sentence is a token. Also, punctuation is also a token. And that by itself has its own interesting applications. But let's say for each of the word as a token, it's going to have a corresponding activation vector at a particular layer, which is actually corresponding to the embedding of that word in a high dimensional space. So now my high dimensional space is basically the BERT word embedding of those tokens, okay? And then what we do, again, is to apply the same framework and try to study what is the topology in this framework, specifically things like branches and things like loops. What do they mean? In practice, we end up mostly focused on branches in this case, because the branches actually look at very interesting sort of organizational principle among the BERT embeddings. So here is an example, right? BERT is a short for in the BERT, we're actually looking at bifurcation. This is a particular branch we zoomed in. This is a bifurcation of temporal and locative proposition. So we're looking at the word, use of the word in and use of the word on, okay? So here is a branch where on the first part of branch, which I put it in yellow, this is a branch where it contains the word in the sentence where its usage is for dates. So if you look at node A, it says, well, okay, the Roman emperor in 1701, he did something on January 17 or established in the 14th century. So those are the usage of the word in a sentence that is related to time. Same thing with B. All those sentences in B give rise to like the usage of in time, in 2010, in early 2000, okay? But the interesting thing now, if I focus on the pink branch on the other hand, it's still using the word in, except in this case, it's talking about in as in a location, like in Moscow, in Florida, in so-called Rust Belt, okay? So now you see this really interesting bifurcation that actually corresponding to linguistic structure based, as part of the BERT activation, okay? Because the motivation of doing this is because BERT neural network is used for many sort of natural language processing tasks, right? So oftentimes it does really well, and the question is that why is doing so well for certain tasks? And it turns out that even though it's not trained specifically on separating in versus on and all those specific things, it actually has an inheritance structure that capturing the linguistic structures, as almost like a side product during training. So that's sort of an example using BERT. So now let's get back to activation vectors, right? So let's get back to the image classifier. I have this, in this case, I have 9 layers. I'm going to focus on one of those layers. So what is my activation? So we got a question during the break, but I know not everybody heard this. So when you actually have a sort of a convolutional layer, when you input an image, what they do is the image is breaking into a particular patches. In this case, I have sort of 64 patches for this image. So a patch is just a particular sub-region of my image. And at this particular layer, I have 512 channels on this particular layer, okay? And the activation vector is basically for a fixed patch. For example, this patch of this image, which is right here. We're looking at sort of the weights associated with all those channels. And that gives me a vector that has a length of 512, okay? And of course, if I move around this image as I change from patch to patch, this activation vector is going to change. So in our situation for Inception V1, we're probing with 300K images. And then for each image, we actually just sample a random patch, right? But the understanding is that since we sample enough, we probe it with enough images that we're still getting a good representation of underlying activation, even though we're just doing a random patch. Because you might argue among all those patches, maybe the patch surrounding maybe the head of the dog is more meaningful than a patch that is in the background. But we haven't really optimized it in this regard, but still, we're still going to see interesting observation, even with such a random patch. All right. Oh, feel free to interrupt me if you have any questions. So now what's going to happen, let's say a particular image have a number of patches, right? The previous example is 8 by 8. Now, in this case, this is 14 by 14. And we have multiple layers. So for each layer, there's a number of neurons in that layer or number of channels in that layer. For example, layer 3A has 256 neurons. So the point cloud collected there is going to be 256 dimension. Layer 3B has 480 neurons. Then the activation is going to be 480 dimension. So for a fixed layer of the neural network, you're going to collect a point cloud of a fixed high dimension. And we probed it in our experiment with 300 images, 300K images. So essentially we get a point cloud that is of size 300K, okay? And then we're gonna apply the mapper framework to get the summary. So here the math part, I shouldn't, depends on my audience. Sometimes my audience is a mathematician, I put the picture screen, but sometimes I put the picture ice cream, depends on who likes math or who doesn't. So the key part of this is paper back in 2007, and those folks are the ones who also started a company called Ayasti, where the mapper algorithm is at the core, at least at the beginning, at the core of the algorithm that they use for data analysis tasks. So here is a high-level picture, and we'll have a separate lecture that goes into the mathematical notations and everything, but this is a high level. You're going to see a little bit of math in today's lecture. So let's say I have this point cloud, okay? What I would like to do is to get sort of a summary of this shape. So what's important about this shape, okay? It has a head, it has a body. So the head has a loop, the body has a loop, and then it has 2 arms, right? So those are branches. So depends on the resolution, I would like to capture sort of a coarse representation of this shape. So what I'm going to do is, first of all, to capture it, I'm going to cover this point cloud by a bunch of sets in 2D. So the sets I'm going to pick are rectangles. You can take other set, but those are rectangles for the time being. So this is what I call a cover element, this rectangle. It covers a subset of my point cloud, okay? So this is my first cover element. And this is my second cover element, okay? I'm going to denote cover element by U. So U1, U2. And here's my third cover element, and so on. So altogether, I have a number of cover element, okay? Such that the point cloud belongs to the union of those cover elements. Remember, those are rectangles, and I include the interior of the rectangle. So, or think about, I have this point cloud distributed on my table. I'm just covering the point cloud by pieces of paper, okay, until I can't see any point. So that's really what I mean by covering. A covering means that, you know, it's a set where each set contains a subset of my data, such at the end of the day, my data is included in the union of those sets. That's a cover. But in practice, usually your cover element is convex. So rectangle is a good choice, circle is a good choice, and so on and so forth, because there's something called a nerve lemma. And when your cover element is convex, there's a really nice property. Okay, so this cover is also hopefully will remind you of what we learned last lecture on sensor networks, right? Sensor network ultimately is also a cover scenario, except the space you want to cover is in entire sort of R2, is the entire plane, right? Here, I only need to cover my point cloud, okay? So now if I have this cover of my point cloud with a bunch of rectangles, I'm going to obtain what's called the nerve of the cover. So what is a nerve? The nerve is that each cover element now become a node. So it's a nerve. In this case, it's a one-dimensional nerve. So it's a graph, okay? So each cover element, for example, the cover element U1, this cover element U1 became an orange node, 1. The cover element U2 became a node 2, right? So this is my 2, and so on and so forth. So each of the cover element became a node. And then there is an edge between a pair of nodes if their corresponding rectangle contains element from my point cloud. So they have non-empty intersection. So for example, in this case, my cover element, let me just use my cover element U1 overlap with my cover element U2, where the intersection, I'm going to color it in pink, right? So that is intersection. So as long as two cover element has non-empty intersection, there's an edge between them. So in this case, there's an edge between 1, 2, there's an edge between 1, 3, and let's do one more. There is an edge between the green. Oh, that's not the green. There is an edge between the green node and an edge between the purple node. Well, actually, this is pink since I don't have purple filling. So there's an edge between them because they have non-empty intersection. Okay, so that is a definition of a one-dimensional nerve. So only care about pairwise intersection. If I care about three-way intersection, that became a two-dimensional nerve. And we'll come back to that later. So right now we only care about one-dimensional nerve. So you say you cover my point cloud by a bunch of rectangles, and then when there's each rectangle cover element became a node, and then there is an edge between them if they have non-empty intersection. All right, so that is my skeleton. But this is not the entire story yet. But what's good about it is that if I know how to choose a cover in this case, right? If I know how to carefully choose this cover, I can obtain a summary of my point cloud on the right-hand side, which preserves the arm, the loop surrounding the head, and the loop surrounding the body, okay? So it's a good, in some sense, a coarse, but pretty reasonable representation of my original point cloud because it preserves some of the interesting features that I'm interested in, okay? But now let's look at what the mapper graph does. So one of the main question is, in order for me to get the one-dimensional nerve of a cover, I need to have a cover first. So how do I obtain this cover? So the way to obtain the cover from the mapper framework is based on a function defined on this point cloud. In this specific case, I can choose a function that is just a height of the point cloud, right? So basically it says the node at the bottom has a very small height and the node on the top has a very large height. So basically you just have the snowman standing up on the ground and you say that I'm going to assign a height to every single point in my point cloud. So now using this height, I can derive a reasonable cover of my original point cloud. The way to do it is to say now my point cloud is my x, and I have a function f, which is my height. And I'm going to just, write it like this so that we know it's a height function. And the first thing I do is I look at down the height function. I'm going to start with a bunch of intervals that cover a range of the function value. So basically I have a function f, and f of x captures, right, the range of the function. So the smallest function value, the largest function value, I would like that to be covered by all those intervals. I is equal to 1 to 6, so I use a 6 cover element on the real line, right? So they're basically intervals that have some amount of overlap, okay? You want the overlap because you want the entire real line to be covered by those intervals. And because also I would like to induce cover element from the point cloud that has some overlap. So that's why we start design those cover element as overlapping intervals. And now the next step to do is I'm using those interval to obtain a cover of the point cloud. So what do? Is I look at the inverse map of this interval. So f, this notation here is the inverse of an interval. What it does, it returns all the point cloud who has a function value within this interval. So this corresponding to all the orange node that I'm highlighting, okay? So all those orange node has a function value in this interval, okay? So this is where I'm going to construct my cover element. So I'm saying that now my first cover element, okay, is capturing the sort of a cluster of points in the inverse map of V1, okay? So this is my first cover element, which is inverse, which is a cluster of points in the inverse of V1. Now, if I start with a second one, I'm going to focus on the cover element V2. And what's going to happen in here is when I take the inverse map, I'm going to get all the, let me use this highlight color. It's going to get all the blue points, okay? But in some sense, those blue points, they're all in the inverse map of V2, but there's actually roughly 2 clusters of them. So I'm going to derive 2 cover elements that cover those 2 clusters. So in practice, how do you do this? In practice, you have a point cloud and you have a cover that you defined, which is a set of intervals. For each of the interval, when you take the inverse map, you get all the points whose function value is sort of within this range of values. Then you apply some sort of a clustering algorithm. And then the particular clustering algorithm people like to use can be, say, single linkage clustering, or can be things like dbScan. So if you have not heard of a dbScan, it's just another clustering algorithm based on density. So I only group points who are densely, in a dense region of each other. So in this case, if I look at all the green points in the original point cloud, there's 2 clusters because there's 2 densely in dense regions, okay? Similarly, if I move on to, say, the third cover element, see this red piece, V3, I'm going to look at all the inverse map of it. And in this case, in the inverse map, well, I'm just going to use pink since I don't have this color. It's going to be all the points that I just colored. Again, you apply the clustering, you get 2 clusters, okay? So this is how you obtain the cover element. Once you have the cover element, you apply the one-dimensional nerve. Again, the 2 cover element, there is an edge. If they have non-empty intersection, you obtain the right picture, all right? So of course, there is a few details that, I haven't goes into describing. First of all, if I have real world data, right? Let's say now this point cloud is my activation vector. It's high dimensional point cloud, right? There's no specification that this has to be happening in 2D, right? I'm just using 2D as example. So let's say I have a high dimensional point cloud. The first thing to do, so that is my data X, right? That is my data, is my high dimensional point cloud. So potentially this is R of D, where D is bigger or equal to 2, but D can be, in our case, D is equal to, for example, 512, okay? The first thing is, what is this function, okay? In this example, I'm using function that is a height function, but in my study of the neural network, I'm going to use a function which is L2 norm, which is basically computing sort of, in some sense, the magnitude of my vector, right? So L2 norm of the vector. And the argument is if the neurons are reacting strongly to a particular image patch, then it's going to have a very high norm versus a very small norm. Okay, so that is part of the argument. So I'm using L2 norm. But this is the first variable, which is what is a function defined on my point cloud. Then the second thing, which is related to this cover, right? In this case, how many cover elements? So in this case, I have 6 cover elements. And how much overlap do I want the cover element? When I say cover element, I'm talking about cover element of the real line. Okay, so in this case, I have 6 intervals. And then roughly they overlap 33%. So the other variable is number of intervals and percentage of overlap. Okay. But also what's hidden is once I take an interval, I take the inverse map, what is my clustering method, right? I'm using dbScan. So dbScan is a choice of clustering methods, okay? But also inherently, whenever I'm doing clustering, I need to be able to compute pairwise distances between the points. So you have to define how do you capture distance between my original point cloud. In this case, we're using Euclidean distance because they are vectors, and we're just going to compute Euclidean distance between those vectors, okay? But you can do other distances as well. All right, so now you start with a point cloud on the left, and you end with a summary on the right. As I mentioned before, it captures the branches and also captures the loops. But the last bit I want to mention is something we are going to come back to it. It's very important how many intervals you're going to choose. Because if I just choose, say, very extreme scenario, if I only choose 2 intervals, all right, then my topological summary of it, of my slow man, is just going to look like a line. Or it's going to look like a graph with 2 nodes. The top node is my blue nodes, and the bottom nodes is my red nodes. And that is my summary, okay? So this is a very coarse summary because it doesn't capture any of the other information. It just says there's an object that is standing up, okay? And if you actually refine this and increase the number of intervals going from 6 to like 16 or 600, you're going to capture more and more interesting information, except at some point, you are not going to be able to connect those cover elements any longer, okay? So you might start getting some disconnectivity because when you are too fine, remember I have a very coarse point cloud. At some point when my interval is too refined, I'm also going to start losing the connectivity approximation I'm obtaining by having the right level, okay? So all those are parameters.
There's a question in the chat asking if this is how the bifurcation graph from earlier were created.
Exactly, this is how it's created, right? This now here is a potential bifurcation. This is a bifurcation right here, right? This is exactly how it.
Are you actually using the height function though, or is
No, I'm using L2.
L2 function, okay.
L2 norm. Yeah, for our activation vectors, I'm using L2 norm. So, okay, so let's get back to the pipeline, right? The middle picture here now, this is now my activation vectors in 512 dimension. And I'm going to pick some intervals and some overlap, and I'm using L2 as my function, and this is what I get. And this is another example. This is an interesting bifurcation too. So this is a particular layer I forgot which layer it is, but this is what I call a face leg bifurcation. I don't know why it's there, but it's actually humanly interpretable to some degree. Is that on the left-hand side, if I go along this, all the images on the left branch, okay? All the images are sort of animal images. And for example, if I focus on node A, it contains activations coming from horse and dog and everything. If you look at the feature visualization, again, it's sort of optimized futuristic image that give rise to the average activation. It captures something like a leg, okay? And then now if you look at the right branch, for example, looking at this node B, it contains images that are coming from human faces, okay? Those are feature visualization. Again, it's a little bit creepy. You see the eyes and you see the nose and everything. So you have some sort of facial features, okay? And then if you go back to the branching node right here, this is a mix of animal images and human images. I mean, the feature visualization still mostly capture faces, but if you look into those images, it basically contains like sort of human images with a whole torso, which include the leg kind of feature and also include sort of elephants. Again, you have sort of leg features. But in some sense, this is what we call a leg face bifurcation, which happens in the probe image net. The other example are things like what we call wheel tread bifurcation, right? So on one branch, in the left branch, BCD, this is very much look like the, they're all, this is whole area that is images from basically cars with wheels. But if you look at the, again, at average activation, they are all looking like wheels, specific wheel-like features. So the wheel of the car, okay? So, and then this is called the wheel feature. And then the other one is like tread-like feature. So if you look at feature visualized images, it's much more focused on like things like texture and sort of like tread-like things. So it's an interesting separation between the feature associated with the tire of the car that is picking up, one is picking up the sort of circular loop and one is picking up sort of the tread-like patterns and textures. And
so
yeah, go
I
ahead.
have a question. So
Yeah.
a branch in this context is like a separation between two classes. So what does
Yes.
a loop mean? Is it like?
Yeah, we'll come get to it soon. For me, actually, I think loop is a little bit interesting. I hope I have at least one example of the loop. You'll see that soon. The loop in certain inspection, I have to claim that it's a little bit speculative. In certain example, you will see it's coming from different parts of the same animal. Okay, so now there is an argument like, okay, what's the difference between my mapper graph, which is on the right-hand side, versus some sort of dimensionality reduction techniques, right? So right now, what we see is that all the yellow point in here, all the yellow point are the points that belongs to this leg face branch that is in this area, okay? If I do just dimensionality reduction of this point cloud, right, I would not see this branching structure at all, right? It's completely hidden from it. So one of the major argument of using kind of topological tools here is trying to pick out fine level shape of this high dimensional point cloud that cannot be obtained through traditional dimensionality reduction, right? Because you can't project this point cloud and hope to see this bifurcation. However, what you can do is that if I just pick out the nodes from this area, and even if I just do a PCA, you will see that those point cloud coming from the branchings actually project in roughly two different dominant direction, which basically is a good indication. I mean, this is not a proof, right? But it's a good indication that the point cloud that form this bifurcation in the original high dimensional space are indeed have some form of bifurcation, okay? So you can do the same thing. For example, if I just do PCA of those 2 point cloud with respect to entire 300K points, you see something in the left. But if I take those point cloud belongs to the leg and face bifurcation, and I take the neighboring points, only take the nearest neighbors points, you see some, you also see some bifurcation. So basically, this is just a verification that in the neighborhood of those branches, when you just take the points in the neighborhood, you will see that there's some sort of two different dominant direction that those things are forming, Okay, and that's what the macro graph is trying to capture. It's trying to recover this branching structure in the original high dimensional space. And then when you visualize it, you can see, oh, there's a branch in my original high dimensional space.
I have one question.
Yeah.
So how do you visualize the point cloud in the beginning of this?
I don't visualize a point cloud, right? This is just an example where I'm just taking a dimensionality reduction of the point cloud. This blue point is just using t-SNE, which is a dimensionality reduction. In our tool, we don't really focus on the point cloud itself. We focus on the summary of the point cloud, which is this graph.
I see.
Yeah. All right, so let's move on, right? So you can also sort of study self-similarities in areas which I'm not going to go into detail. You can look at global activations, but also you can do this over different layers, right? So those are the summary, of course, at a fixed parameter across different layers, okay? There's 9 layers of inception V1. And you can do the same thing with CFAR10, right? CFAR10 is trained on ResNet. So ResNet, we only probe five sort of layers, okay? So this, in addition to the horse-deer bifurcation, in ResNet, the last layer, you also see some sort of frog-cat bifurcation, okay? It's kind of fun for me when we look at this, is because, okay, so why do they bifurcate between those two classes? I mean, if we look at the images, is in some sense that the posture of the frog sometimes looks like the posture of the cat, right? They both sit down, they both have sort of body in a certain position and so on and so forth. That's why those two classes have this kind of bifurcation, which is fun. So now let me, with the remaining time, talk a bit, right? This is not constrained to an image classifier. You can apply this to a text classifier like BERT, right? And BERT has been used, like I said, with a lot of NLP tasks. And usually it's very useful in improved predictive accuracy, but it's not clear why it works so well. So that's because those BERT embedding, which is those embedding of a single word in a sentence, this is what we call activation vectors. They consist of a collection of, again, high dimensional vectors for every single sentence, and this become kind of hard to explore. So in our scenario, we're probing the BERT network with close to 5,000 sentences, and that corresponds to 80,000 tokens, right? The tokens include the words and then things like punctuations. And then what this framework does, it will help reveal sort of different syntactic and semantic meaning that the BERT capture. So I already gave an example earlier. Again, this is how the interface looks like. This part, we haven't made it open source yet, just because the data set below is really big. But this is how it looks like. Again, if you zoom in, this is on the left-hand side is the global summary of the BERT at layer 9. And then if you click on a particular node, it's going to tell you which sentence give rise to the activation, which word in which sentence give rise to that activation. And this particular node I choose just happened to be some word that related to the year that give rise to activations, okay? So a few more examples, right? Again, this is an island, actually. This is an island from the mapper graph. And this island has to do with the word me and the word my. They are what's called first person singular pronoun versus possessive form, right? So if you look at, node A, node B, node C, they are roughly, like for example, this branch, BC, they're roughly focusing on the sort of me, right? She invited me, she looks at me, Pete looks at me, and then, A is me, and then B is a use of my. B and C are both usage of my, right? So this is more of my dog, my mother, my old heart, and my autograph. But there's an interesting usage here, which I think is quite fun, is that I was riding me bike, okay? So you're thinking like, why is this in this branch, right? Because all this branch, the rest of it is using my, right? Like possessive form. But all of a sudden this word me is in there, but me is like, okay, he invited me. But this turns out to be, our guess is sort of like a local dialect. When they say, I was riding on me bike, in the local dialect, it really means I was riding my bike. because they're using me as if it's a possessive form. Okay, so this is really interesting because you are actually looking at distinction between the meaning of the words as well as how they are used in a grammar way, right? Like how is it fit in a sentence? Okay, so this is the first example. So you can differentiate different pronoun. The other example is sort of a contextual example. Again, this is an area that I focus on. This is like a large, like, part of a graph, but I'm just focused on one small area. This whole area has to do with water, right? So the area on the left-hand side from A, you see things like sea, marine, sea, wave, and things like that. So both A and B, in some sense, has to do with sort of oceanic usage of the water. And then you move on to C. C now is to say, okay, water began to swirl down the drain, water balloons in cold water. So it's still kind of related to ocean, but you kind of move a little bit away from just weather-related thing. But then if you move on to D, which is quite interesting, you're looking at how water is used in cooking. For example, 2 cups of water or broth. And then because you are using cooking land, you are then moving on to the usage of oil, right? Because that's also another liquid that is used in cooking. So it's sort of like it's kind of morph in this area of how water is showing up in weather as in the ocean, then in weather, and then in cooking, and so on. And I can tell you if I move this further, it's more of a culinary usage and so on. Okay. So this is what's called contextual differentiation. Like, what is the context of the word water or something similar to water shows up? This is another example that has to do with art, okay? So in this case, this whole area has to do with artwork. So from A is like artwork museum, going to B, a display exhibition, going to C is images, going to D is things like shot and photo. And if you move to E, E is like prints, and F is like photography. And one thing I didn't note is actually this area, which I didn't note, those are videos, okay? So again, you're looking at sort of word knowledge that is in this area. I mean, everything that is in this neighborhood essentially has to do with art, but then kind of bifurcate into different sort of aspect of art, most to do with photography and artworks and things like that. This is another interesting example. This is in the earlier layer of BERT. What I have showed you is later layer of BERT. In earlier layer of BERT, it's much more syntax. So it's focused more on the words itself than how the word is playing in the sentence. So in this case, I see a branch where this branch, D branch, has to do with impossible, hard, kind of pretty like descriptive words, right? Describing size versus goodness. This branch C from here is starting by talking about most, best. If I keep going, better, 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 and then there's the branch A that corresponds to size, smallest, largest, highest, right? So again, this is a separation more on the syntactic meaning than the later layer of the BERT is more sensation and semantics. I can keep going. And then this is one example where our NLP expert got super excited. I didn't know why at the beginning after he explained to me. This is a separation on the left-hand side, all this side versus the right-hand side. This is a separation of the usage of the word when, okay? So apparently there is a very difficult thing to separate the usage of word when and if. When is to introduce discourse, and both of them is kind of convey temporal meaning, but they are very distinct in the BERT embedding. Okay, so the idea from the NLP expert is that it's developing further parser for discourse or sort of structure of the text. So this is something very exciting for the NLP expert, like to pick up very fine level detail of how these words are separated in their usage in sentences. So I can keep going on forever. Okay, so so my slides here does not have an example of a loop. But I will, at the beginning of next lecture, I will show an example of a loop. So the loop is basically when you see a loop, especially image classifier, we have examples of a loop where it's different parts of a bird. Like it starts from sort of the peak, the eye, you know, and if it's a loop involving sort of mammals, then it's sort of the eye, the nose, and different aspect of the view. But however, I must say that the loop is much more speculative. Because there are certain reasons, certain loops may not be that meaningful. And that has to do with sort of the J-car index between different clusters. And we can go into some of that detail later too. All right, so you can actually play with this on the image side. Oh, it doesn't copy at all. You can actually, oh yeah, of course. You can actually free to play with this. And for example, you can play with, this is a Inception v2. Oh, sorry, Inception, oh no, this is not Inception, this is ResNet. And you can change sort of the parameters. And you can kind of, because I haven't really done it on the iPad that much before, and you can look at essentially, you know, right? This is all the dog images in here, and you can also play with all the branches. So it's better on an actual mouse computer, but you can play with it. And then there's definitely some open questions surrounding this, right? For text classifier, you can look at sort of this structure, linguistic structures, and it can give you idea how to, like, why is bird behaving well for certain linguistic tasks. And this is one of the direction we're pursuing right now. But there's also the discussion of confirmation bias, right? This is something like, am I always looking for what I'm looking for? So I'm geared towards looking for certain things. It's certainly there, right? But as you can see, especially from the bird example, as well as sort of the deer, horse examples, that there is a connection between the classification versus sort of the activations that is coming from those images. Of course, this can be generalized to any other neural network architecture. There's always a question of the parameter tuning, and which we are going to talk more when we go into the mapper framework, right? You have all these parameters. How do you choose the right parameter to get the right thing? And then there's also the conversation about scalability, which is, well, I have 300 images, right? I mean, we actually went up to, we can now go up to 3 million for the mapper framework, but there's also a limit of how long it will take to compute those maps. And lastly, there's always this theoretical discussion. I just put one example here of the stability of those structure, meaning that if I change my cover element, if I change my parameter, how stable is my topological structure? You want it to have some stability, because then your insight you get is sort of have some sort of confidence, right? Because the structure is stable. So there's a lot of discussion surrounding this structure, but this is sort of my first example of how how topology can be used to study activation vector from neural network. Okay. All right, I'm going to stop streaming and then